Hi, my name's Harry.
And I'm Mark. In this video we'll be discussing Dantzig's simplex algorithm, how it works, how to use it, and then briefly discuss its time complexity.
Dantzig's simplex algorithm is an algorithm that finds an optimal solution in a linear programming problem. Now, what is a linear programming problem, I hear you ask? A linear programming problem is a problem that involves attempting to maximize or minimize a certain objective function of a set of variables. For example, here we are trying to increase this function with respect to x, y, and z. We do this subject to a set of linear constraints. These can either be equality constraints or inequality constraints. These constraints describe what is called the feasible region, i.e. the set of solutions that satisfy the constraints.
For the simplex algorithm to work, the linear program must be in standard form. This means that it is a maximization problem. Each constraint must be less than or equal to an inequality constraint. Each variable must have a non-negativity constraint. If it's not in standard form, it must first be converted. Here I will demonstrate how to convert an example program to standard form. First, if it is a minimization problem, we must convert it to a maximization problem. To do this, we just negate all of the variable coefficients. So 2x plus 7y plus z becomes minus 2x minus 7y minus z. Next, we require that all the variables are greater than or equal to 0. So for every variable that is not constrained to be greater than 0, we instead write it as two new variables, both positive. As you can see here, x becomes x1 minus x2, with x1 and x2 more than or equal to 0. Now we replace any equalities with two new inequalities. So x1 minus x2 minus z equals 7 becomes x1 minus x2 minus z is less than or equal to 7, and x1 minus x2 minus z is greater than or equal to 7. Since two of the inequalities are greater than or equal to a constant, we need to modify them so that they are less than or equal to that constant. To do this, we negate all the coefficients and make their sign less than or equal to. Finally, we want to replace z with a new variable so that all the variables are greater than or equal to 0. We add in u and have it equal to the negative of z, then replace all the z's with minus u's.
Now, Mark and I feel that the best way to understand simplex is through an example. Consider this objective function. You can see that it can be increased by increasing x or by increasing z, but not by increasing y, since its coefficient is negative. This idea is essentially the basis of the algorithm. By observing the objective function, we increase the relevant variables as much as possible while still satisfying the program's constraints. To demonstrate the simplex algorithm, we will be solving this linear program, which is already in its standard form. To begin with, we must first put the program into what is called its slack form. To put the LP into its slack form, for each inequality, create a new slack variable equal to the right side of the inequality minus the left side, as you can see here. Notice how we have written these new variables into the objective function. Also note that they must be kept positive as a result of the inequality constraints. With the linear program in this form, we call the variables on the left the basic variables, and we can find an initial feasible solution by setting the non-basic variables to 0. So we have u equals 6, v equals 2, and w equals 2, with the objective function equal to 0. Now, let's take a look at the objective function for a second. Clearly, if we were to increase the value of x, we would be increasing the value of the objective function. So, let's increase x. In the process, x will become a basic variable. Notice that while we could do the same for z, we could not, in a similar way, decrease y, as it is already 0 in the initial feasible solution, and it must remain non-negative. Let's see how much we can increase x by. Now bear in mind, u, v and w must be kept non-negative. In the first constraint, x can be a maximum of 6. In the second, we can increase x without bounds. because its coefficient is positive. In the third constraint, x can be a maximum of 2 over 5, as 2 minus 5 times 2 over 5 equals 0. Since x must be chosen in a way that satisfies all of the constraints, we choose the minimum of these values, which is x equal to 2 over 5. This is in the third constraint, so we will rearrange this so that x is basic. As you can see, we have rearranged the third equation so that x is now the basic variable in this equation. Since we now have x on its own on the left-hand side, we can substitute x into the other equations, as well as the objective function. Now, let's see what we get when we expand these equations. Now, we have u, v, and x as the basic variables. Like before, we can set the non-basic variables, which are now y, z, and w, to 0, and u to 28 over 5, v to 14 over 5, and x to 2 over 5 to get a new feasible solution. Also, if you plug these values into our reformulated objective function, you'll see that it has increased to 2. Clearly, we are on the right track. We have just completed the first iteration of the simplex algorithm, where we have maximized the value of x. In the process, x has become a basic variable, and the value of the objective function has increased from 0 to 2. We are now going to repeat the process and increase another variable. Take a look at the objective function again. Which variable do you think we are going to increase the value of? That's right, we will increase y, because it has a positive coefficient in the objective function, so increasing it will increase the objective value. Now, like before, we will look at the maximum we can increase y by, keeping u, v, and x non-negative. In the first equation, y can be a maximum of 1. In the other two equations, we can again increase y without bound. So, like before, we will now rearrange the first equation so that y becomes a basic variable. And again, we will substitute this into the other equations and the objective function. And after expanding the brackets, now y, v, and x are basic, we have another feasible solution, and the value of the objective function at this feasible solution is now 8. Now, one last time, let's take a look at that objective function. Can we increase it further? No. The coefficients of z, u, and w are all negative. Increasing any of these will decrease the value of the objective function. Therefore, the solution we have is an optimal solution. Let's check our new optimal solution, only considering x, y, and z, in the linear program in its original form. As we can see, our solution satisfies each of the original constraints, and the original objective function is 8. We have successfully used simplex to solve this linear program. So let's summarize how to use the simplex algorithm to solve a linear programming problem in its standard form. 1. Convert the linear program to slack form. Remember, we do this by subtracting the left side of the inequalities from the right and setting the result equal to a new slack variable. 2. Examine the objective function to find which variable to increase by looking for the variable with a positive coefficient. 3. Examine the constraints to find the equation in which to make this variable basic. We did this by looking at the maximum value this can take in each constraint. 4. Solve for x and substitute into the objective function and constraint. From this, you can obtain another feasible solution. 5. Repeat 2, 3, and 4 until all objective coefficients are less than or equal to 0, in which case you have found an optimal solution and the algorithm stops. Well done. Let's discuss the computational complexity of simplex. Let d equal the number of variables and n the number of constraints, which, including the non-negativity constraints, is more than or equal to d. In the worst case, simplex can run an exponential time. This is because, in geometric terms, simplex works by moving from vertex to vertex of a polytope in d dimensions, where each vertex represents a feasible solution of the linear program, until it finds an optimal solution. This polytope can have a maximum of 2 to the n vertices, and so simplex can have up to 2 to the n iterations. However, most of the time, simplex will, in practice, run in polynomial time.
Thank you for watching our video on Doomsock's simplex algorithm.
We hope you have both enjoyed and learned from our presentation on Dantzig's simplex algorithm.
And remember, it's not too hard, it's simple.
Let's